And the chapter 16, we're gonna looking at alcohol. So the alcohol is actually something we learned already in organic one. We learn a lot about alcohol, but we will be learning something new about alcohols in this chapter. The source of alcohols, you know the just you guys read it. But I guess the two most important alcohols, methanol, three most important alcohols, methanol, ethanol, and isopropanol. And isopropanol is probably because of the, it's relatively easy to prepare, and also can be used in the medical application, similar in ethanol. And and ethanol, we all know that the human has a long history of consuming it. And actually, I checked it. It's very surprising. How long is the history human has been consuming alcohol, ethanol? 10 million years. Even before human existed, meaning the ancestor of human, not really human, like those the apes, monkeys, even before human existed, they already start, our ancestors already started consuming alcohol. Obviously naturally, those are, you know, rotten fruit, falling on ground, they undergo natural fermentation process. They had, create alcohol. Then accidentally, a sister of a human pick it up. So anyway, that's the alcohol. And then the reaction that can form alcohol, we already learned many such reactions in organic one. One is the acid catalyzed hydration of alkenes. We learning organic chapter 8, organic one. And the hydroboration oxidation also is chapter 8, organic one. So this reaction often involves the carbocation, and this reaction does not involve carbocation. So that means technically this guy could involve carbocation rearrangement if it's feasible. But this guy will never undergo carbocation rearrangement because carbocation is not involved. Okay? So and also that's why the when the alcohol, the two double bond, not alcohol, the two double bonded carbons, they have the different substitution. You will see the alcohol formation, residual selectivity of the formed alcohol follows Markovnikov rule, and this one, the alcohol product opposite to the Markovnikov rule. Like here, the two double bond carbon, the OH group add to the less substitute carbon. Okay, but if you do the acid catalyzer hydration, the OH group will connect to the more substituted carbon. So let's say if you have if you forgot the reason, go revisit the chapter 8 content. So let's say if you have acid, water, you will get this alcohol, okay? Not this alcohol. Okay. So the check what you learn in chapter 8. And also alcohol can be prepared from the alkyl halide by hydrolysis. Depending on what kind of alkyl halide we have, if it's a primary alkyl halide, so it could be SN2 reaction. If it's a tertiary alkyl halide, that will be what reaction? If it's tertiary alkyl halide, reaction with the water give you alcohol. What kind of reaction will be mechanism-wise? Yes, SN1. Because the tertiary alcohol at SN2 is completely shut down because unusually large steric hindrance. So only SN1 is possible. And we just learned in chapter 15, alcohol can also be prepared by organometallic compound reaction with carbonyl compound. So if you react with formaldehyde, you get a primary alcohol. react with the regular aldehyde, get a secondary alcohol, react with ketone, you will get the tertiary alcohol. So those are the reactions we have learned already. Okay. Now we're gonna learn, a new type of reaction is alcohols can be prepared by reduction of aldehyde and the ketones. And the first kind of reduction method we will be learning is catalytic hydrogenation. So we know in aldehyde means one side of the carbonyl connect to hydrocarbon group, the other side connect to hydrogen. This is called aldehyde. Okay? And if both sides connect to hydrogen, we call it formaldehyde. Formaldehyde is a special kind of aldehyde. But say conventional aldehyde has one hydrogen connect to the carbonyl. Okay, so sometimes you can call this part called aldehyde group. So the hydrogen connect to carbonyl, we call aldehyde group. Okay, so the key functional group in aldehyde or ketone is the CO double bond. And the CO double bond, just like any double bond, it has a one sigma bond plus one pi bond. And the pi bond, again, I hope you recall what you learned organic one. Pi bond is generally weaker than sigma bond because sigma bond there is two orbitals head to head overlap. So that overlap is have a larger volume overlap, give you a stronger bond. And the sigma electrons, if these are two nucleus, the sigma electrons, bonding electrons, they are hidden. They are in the middle of the bond axis. They are more difficult to be accessed by reagents. But the pi electrons, they are basically shoulder to shoulder overlap. The overlap is above and below the bond axis. So the pi electrons, they are more exposed to potential reactions. So the pi bond generally much more react than sigma bond. So here, one reaction you can happen is let this CO double bond, one more of CO double bond, will be able to react with one more of hydrogen. And the next reaction is the carbon and oxygen both will get the hydrogen. Okay, carbon gets the hydrogen, convert the CH to CH2. O gets hydrogen, becomes the OH group. And then the pi bond is no longer there. So if you consider the energy of this hydrogenation reaction, basically you break a carbon-oxygen pi bond. You break a carbon-oxygen pi bond, and you break a hydrogen-hydrogen bond. So you break a carbon-oxygen pi bond. Okay. You break a hydrogen-hydrogen bond. And what you get a CH sigma bond, and you break, okay? You form a CH sigma bond, okay? And OH sigma bond, okay? So for all the carbonyl compounds, this reaction almost always ectothermic because you're forming two sigma bonds. And you're breaking one sigma bond and one pi bond. Okay? So it's a good deal for the hydrogenation to happen. And just like hydrogenation we learned in Organic 1, Chapter 8, hydrogenation usually requires catalyst because hydrogen-hydrogen bond is kind of pretty strong covalent bond. You need a catalyst to break the hydrogen-hydrogen bond. So all those catalysts, platinum, palladium, nickel, or rhodium, those metals can form, metal hydrogen bond and help to break the hydrogen-hydrogen bond. That's why they are very powerful catalysts for catalytic hydrogenation. So the reaction happens on the surface of catalyst. So the reaction is pretty straightforward. You just add the two hydrogen atoms, of course, carbon, oxygen double bond. That's why, one bond, the CO double bond has one sigma bond on pi bond. So each pi bond can react with one more of hydrogen. So that's why we can using complete hydrogenation to tell how many pi bonds we have in a molecule. So when there are multiple pi bonds in a molecule, the aromatic pi bonds, like here, those double bonds, they are generally much more stable than those pi bonds outside of the ring. So you can selectively hydrogenate the double bonds, non-aromatic pi bonds, and the aromatic pi bonds can be, the retained. Okay? So basically, you can control the hydrogen pressure, the control the temperature to limit hydrogenation to those pi bonds outside of aromatic ring. Besides catalytic hydrogenation, we also can using the kind of reducing reagent called metal hydride reducing reagent. So one of the trouble of catalytic hydrogenation is we have to use hydrogen gas. And the catalytic hydrogenation is highly preferred at industry scale, but it's highly, usually we try to avoid hydrogenation in the laboratory because of the, in a lab we often, have to work with students. Not all students are extremely careful. And the problem is if you're dealing with hydrogen cylinder, if you're not careful, it could be end of one of the person involved because hydrogen are easy to undergo explosion. Okay? So that's one of the reasons, we want to avoid using hydrogen cylinder in a typical lab. So then if we want to do the reduction, we can use something else. Generally it's a solid. Okay, it's so it's easier to not like hydrogen. It's a gas. It's less likely to undergo explosion. So the two commonly used reduction compounds called sodium boron hydride and lithium alumina hydride. If you look at the structure, they're actually highly similar. This is lithium alumina hydride. So this is the positive part, this negative part, and the other one is sodium boron hydride. So both these two guys, they are reducing agents. The lithium and the sodium ion, again, you can treat them as spectator ion. So the key reduction, the part of the responsible for the reduction power is AlH4 minus and the BH4 minus. Okay. So these are the two key reducing reagents. And if we can guess which one has a greater reduction power. Well, both are negative charged, right? Which one has a greater reduction power? Alumina sits below the boron, so alumina should be less electron negative than boron, right? Just general periodic rule. So alumina is more reductive than the boron. So that's the thing you need to pay attention to. So the top one is a more powerful reducing agent than bottom one. Okay? So powerful not always means the best. Okay, we will see the difference and the similarity of these two reagents. But the first one is more powerful, the lower one is less powerful.